A factory manufactures aluminium rods. One of its machines can be set to produce rods of a specified length. The lengths of these rods are normally distributed, with mean equal to the specified length and standard deviation equal to 0.2 millimeters. The machine has been set to produce rods of length 40 millimeters. So this is the specified length, this is the mean. We're given that the mean is equal to the specified length. The standard deviation 0.2 millimeters, that's sigma. Part A. What is the probability that a randomly selected rod will be less than 39.7 millimeters in length? So we're dealing with a normal distribution. So it's a normal distribution with a mean of 40. That means it's centered at 40. The standard deviation sigma is a measure of the spread of this normal distribution. Sigma is 0.2. So we're interested in lengths that are less than 39.7. So let's suppose that 39.7 is here. It's probably closer to 40, but just to make it easier to read. So this here is our x-axis. So x is length of rods. So the random variable x, capital X, stands for the length of a rod that's selected randomly from our population. So we have a population of rods with a mean of 40 and a standard deviation of 0.2, and we want to find the probability that a randomly selected rod will be less than 39.7. In other words, we want to find this area here. So I've explained this in other videos. What you need to do is convert this to a standard normal distribution. That is a normal distribution with a mean of 0 and a standard deviation of 1. The way we do that is to convert our x value to a z-score. This is like our x-score. We use this formula here, x minus mu divided by sigma. This is essentially the number of standard deviations that x is from mu. X minus mu is how far x is from mu. If we divide by sigma, that gives us the number of standard deviations that this value x is from mu. So this is sometimes called the z-score. So we have 39.7 minus 40 divided by sigma, which is 0.2. So that's minus 1.5, so I'll mark that on our standard normal distribution. So this horizontal line here is the z-axis. So I want to mark in minus 1.5. It's to the left of 0 as expected. 39.7 is to the left of 40, or less than 40. So what we want to do is get this area here. So that's where we go to our standard normal distribution tables, or what's sometimes called the z-tables. Now, these particular tables give us the area to the left of positive z-scores, whereas here we want the area to the left of negative or minus 1.5. So what do we do? Well, we have to consider the area to the left of plus 1.5, because only positive z values are tabulated here. So what we've got to do is consider this area here by reading a z value of 1.5. So here is 1.5, and to 2 decimal places it is 1.50. So these tables here give z values to 2 decimal places. So we go to 1.5, which is the first decimal place, and we read under the second decimal place, so we read under this. Okay, because we want 1.50. If we wanted 1.51, we'd read in this column here. So here's the value. So that's this area here. It's 0.9332. Okay, so that tells us that the area in this tail here is 1 minus 0.9332, because the total area under a probability distribution, a normal distribution, or any probability distribution is 1. That area is 0.0668, which is the same as this area here by symmetry. So we're exploiting the symmetry of our normal distribution in order to be able to read the tables. So putting this together now, x is the length of a rod. The probability that a randomly selected rod has a length that is less than 39.7 is 0.0668. Another way we could interpret this is that if we have a large population of rods, then this fraction of them, or if you like 6.68% of them, we write this as a percentage, have lengths that are less than 39.7 millimeters. B. 5 rods are selected at random. What is the probability that at least 2 of them are less than 39.7 millimeters in length? So we're dealing with a binomial distribution here. The number of rods that are selected at random is n. That's the parameter n in the binomial distribution. The probability that one of these rods is less than 39.7 is 0.0668. That's the parameter p in the binomial distribution. So that means that the probability that a rod is greater than 39.7 is 1 minus p, which is 0.9332. So we have 5 rods selected at random. Some of them will have lengths less than 39.7, some will have lengths greater than 39.7. The probability that a given rod has a length less than 39.7 is 0.0668. The probability that it has a length greater than 39.7 has to be 1 minus p, because it's only two options. It's either less than 39.7 in length or it's greater than 39.7 millimeters in length. So we're interested in the probability that at least 2 of them are less than 39.7. So at least 2 means the probability that 2 of them, or 3 of them, or 4 of them, or 5 of them have lengths that are less than 39.7. Okay, so it's 2 or 3 or 4. So we add up these probabilities. So we can do this directly. We can get these directly. Or we can use the fact that if we add on P0 plus P1 to this, we get an answer of 1. Because then we've covered all the possibilities. That is, 0 rods or 1 or 2 or 3 or 4 or 5 rods have lengths that are less than 39.7. So we could do it this way, and then we could say that P2 plus P3 plus P4 plus P5 is 1 minus P0 minus P1. So there's two ways we can do the problem. We can either do this calculation on the left, which involves evaluating 4 probabilities, or we could do this calculation on the right, which involves evaluating just 2 probabilities, P0 and P1, and subtracting from 1. So I will actually do this calculation here because it's a bit quicker. So P0 is the probability that no rods have lengths less than 39.7, and P1 is the probability that exactly one rod, exactly one, has a length less than 39.7 millimeters in length. So now let x stand for the number of rods that have lengths less than 39.7 millimeters. Now this is a different x from the previous x. The previous x was referred to a length. Here x refers to the number of rods out of 5 rods that have lengths less than 39.7 millimeters. The binomial distribution says that the probability that x equals r is ncr p to the power of r times 1 minus p to the power of n minus r. And I explained this formula in greater detail in earlier videos. I explain how this formula comes about and so on, but I won't go through that here. I'll just apply it directly. Now you might use a different notation. Maybe you have a little x here and a little x here. So the probability big X equals little x would be ncx p to the x times 1 minus p to the n minus x. But anyway, that's just to let you know. You might have different notation, but that's not too important. Now we want to calculate P0 and P1. So the probability x equals 0. I can just write P0, meaning probability x equals 0. The number of rods that have lengths less than 39.7 is 0. So that's just NC0, where n is 5. Little p to the power of 0, that's 0.0668 to the power of 0 times 1 minus p, which is 0.9332 to the power of 5 minus 0. 5 minus 0 is just 5. Okay, and then P1 then, we just plug 1 in for R. Get 5C1 times 0.0668 to the power of 1 times 0.9332 to the power of 4. You can see that these powers must add up to n. So 0 plus 5 is 5, 1 plus 4 is 5. So if we calculate both of these probabilities, that's straightforward, and then work out 1 minus the sum of them, we get 0.03895. By the way, to save time, 5C0 is always equal to 1. So that's just 1. And any number to the power of 0 is 1. So we have 1 times this number. So you only have to calculate this number here. Which makes sense, actually, because the probability that no rods have lengths less than 39.7 is, the probability that a given rod has a length, has a length that's not less than 39.7, that's 0.9332. So you want all 5 of them to have this probability. So they're independent events, so we just put 0.9332 to the power of 5